All right, so today we're going to talk about basically core concepts for DBAs. Okay, so this is not going to be a deep dive into some esoteric technical realm, but we're going to be reminded if we're expert DBAs and if we're new DBAs, we're going to be told in no uncertain terms exactly the meaning and the nature of these core concepts called DB time, average active sessions, and ASH, and we'll tie it all up with a section on performance monitoring. So as a practicing DBA in terms of performance management, you really need to understand these concepts thoroughly in order to make sense of things like AWR reports and Perf Hub screens and various of our other tools for managing database performance. So again, my name is John Bereznovich, and I'm an architect in observability and management, and I've been around quite a long time, as you'll see from some of the slides we have here. That's a picture of me maybe a decade or more ago, so more or less look like that now again. Since then, I've had a long ponytail and cut it off. Oracle mission statement. I kind of like the mission statement, so I stuck it in the presentation. Seeing data in new ways is something that I kind of gravitate or identify with, and discovering insights. Unlocking endless possibilities. Nah, I'm not so sure. I posted this on LinkedIn. It got a lot of response. I called it the portrait gallery, but this is basically sort of the grandfathers and great grandfathers of DB time visualizations and over the years, right? So this is sort of the great great grandfather of DB time viz. Maybe this is the grandfather. A lot of people that have been around a while will recognize this because it's a very widely used and popular uh, enterprise manager page. The load map, maybe grandfather level. Okay, maybe this is more like a father level, not too distant past, but not too recent either. That's Ash Analytics. A little different view of Ash Analytics a little later in time. Things change, but they remain the same, right? So this looks very much like the original stuff. Another tree map, and then we have ADDM Spotlight swim lanes, which is a kind of a new visualization of a DB time related thing. So what is DB time? Well, fundamentally, DB time is your time. And what I mean by that is you're a client of the database. You have, Oracle databases service the applications that you use. So in that sense, you're a client of database, and your need for database services come through SQL requests that the database responds to. And sort of diving a little bit into Oracle architecture, but not deeply at all. Clients of the database, your requests, your SQL is serviced by what we call foreground processes. So these are processes on the host, the machine where the database, quote unquote, lives. And these processes, all execute a common code path, and they all attach to the SGA, and they all individually work on SQL queries and together collaborate on things. And so there's a lot of complexity involved. But basically, the time these foreground processes spend figuring out the answers to SQL questions is what we call DB time. It's time that database foreground spend executing client requests. And it excludes idle time, which is really sort of a special class of time that is really doesn't occur frequently, but is not technically part of DB time. And so the other thing to know about DB time is it's the database component of overall total application response time, but it's not the only component. And back when I was a DBA 100 years ago, in client server days, all the people using applications acted as if the database was right behind the screen. Every performance problem had to be a database problem, and there's probably still a lot of that going around, but Applications are much more complex. They have lots of different pieces to them, microservices, this, that, the other thing. So DB time is really only about how much the database is slowing down what you're doing or adding to however long it takes to do what you're doing. And another important concept is that the DB time is fungible. And this issues directly from the fact that it's your time. A minute of your time spent connected to database A or a minute of your time spent, waiting for a response from database B is still a minute of your time. Okay, so that's why it's fungible. And that's a very important property of DB time because it allows us to do comparisons across databases and over time. So in terms of the cognitive model, so-called, of DB time, it looks kind of like this, right? If your DB time is either in one of three states. It's either time spent on CPU doing work or time spent waiting. Those are two states. Well, the waiting state we separate into IO wait. Any kind of IO wait is separated from all the other waits, right? So we usually have the most basic breakdown of DB time is usually into these three buckets: CPU, IO, and other wait. And so IO weights are isolated because they're kind of special. Why? Well, because it's a database. Data is, right, is ultimately lives on disk or some kind of persistent mechanism, and in order to get your hands on it, you got to do IO. So IO is kind of necessary and not necessarily bad, although in terms of managing performance, you want to manage time spent doing IO like everything else. And these other weights are further bucketed down into weight classes that we'll talk about a little bit more in a minute. Oh, another pet peeve of mine is I often hear it said, and even by me, I'm guilty of it too, is that, so and so consumed so much DB time, right? But I don't like that. That's really not the right metaphor because it's not like, the database starts up and there's a big bucket of DB time and people are, taking spoonfuls or bucketfuls, depending out of there, right? It's more like they're dumping spoonfuls and bucketfuls into the DB time bucket, right? So DB time really accumulates. It's not consumed, right? There's not like a big reservoir of DB time that is drawn from, even though that's kind of the metaphor we often use. So DB time is measured in various places in the code, and it actually turns out that we've been measuring a piece of DB time for a lot longer than we've been talking about DB time, and that has to do with wait event timing, which was actually introduced in Oracle version 7, I believe. And these are really just stopwatches in the code that time when foregrounds have to wait for certain things like system calls to complete. And so these are really, best way to think of them as sort of stopwatches in the code that time waiting for things to happen. And in Oracle version 7, the timing was hundredths of a second granularity, but now for quite a while, everything's pretty much been being timed in microseconds. In Oracle 10, where database manageability was a key sort of flagship feature, and many important technologies were introduced, like AWR and Ash, and a lot of tools that basically use those technologies. A lot more stopwatches were added in 10G, similar to the wait event stopwatches, and they go under the name of the time model. And of the time model data, there's two very important measures: the total overall DB time, and also the DB CPU, which is the time spent using CPU. And that latter is extremely important because it's not a stopwatch. It's actually fetched from the operating system and it represents actual time spent executing instructions, right? And these accumulations of DB time are also aggregated at the SQL level. And that basically lets us do very detailed sort of DB time and related analysis by SQL ID. And on the right, you see some of the core data structures in the SGA that have, that contain, expose some of this instrumentation. And then, of course, there's lots of related data structures, AWR, AWR views and tables, and for CPU, there's a bunch of VDOLR views related to Resource Manager that have details. But these are the basic ones. So the method is actually quite simple, right? And we've talked about this for quite a while. How do you, improve database performance? Well, you shrink the DB time. You do what you need to do in less DB time and things are performing better, kind of by definition, right? And so how do you shrink the DB time? Well, that kind of depends on what bucket your DB time falls into, right? So if most of your time is spent on the CPU, kind of congratulations, that's where you want to be, but maybe you can do better by optimizing algorithms, finding out, whether your application is excuse me, wasting CPU, spending excess time using CPU that could be optimized somehow algorithmically. In the case of I/O, well, we got a very good answer for you here at Oracle. It's called use Exadata, right? Exadata makes your blue stuff go away. And then in terms of the weight classes, if you're waiting for other things, well, the classes are really designed to kind of steer you towards solution spaces. If you have a lot of on-queue waits, locking, then that's an application issue that needs to be analyzed. If there's something happening that indicates an init.order parameter is misset, well, that would be kind of a configuration thing, right? So the weight classes are really designed to steer your attention towards the kind of solution spaces for shrinking DB time that might be profitable to pursue. And in terms of tools, these are tools that have been around for quite a while, but the DB time method is really at the core of all these tools, figuring out, how to shrink DB time in the context of a long-running SQL statement for SQL monitoring or SQL tuning advisor, or a collection of SQLs in the case of SPA, or, systemically overall in the case of AWR reports or Perf Hub, and certainly in the case of ADDM. So very important point here, right? Which is if your host is CPU bound or CPU saturated, it basically distorts the timers, the stopwatches. And the way to understand that is basically just looking at this simple diagram. Imagine this is a foreground process over time, moving from left to right. And so, it's on CPU, and then decides it needs to use some data that requires an I/O, a physical a read. So a DB file scattered read wait event takes place. Well, at the start of that wait event, the stopwatch is clicked on, right, beginning the timestamp. And then the scattered read completes, but process is ready to go and use that data and do something else, but it ends up on run queue and then gets the CPU after some certain delay. Well, it requires the CPU to take a timestamp and stop the stopwatch, right? And so that's basically, why the actual latency can be much less than the measured latency. And in the case of very low latency events, this can be an extremely serious thing, right? So, this distortion of wait times under CPU saturated conditions can be a problem when analyzing things. People like to jump after wait events because that looks like time they can save. But if a bunch of it is run queue time, well, hey, your problem is not the wait event, right? And so the best advice is to use Resource Manager, and Resource Manager really helps, kind of control the approach to CPU saturation. It's not a guarantee that you won't be CPU saturated, because there could always be plenty of things going on not under the control of Resource Manager. But it just helps to make the observability much better, right? In a sense, you can think of it as trading very invisible run queue time for very visible schedule or wait time, where you really know how much time you spent waiting on Resource Manager to give you more CPU. So that's a very important point. So let's talk about average active sessions. And this is sort of the all-important concept, I think I said in one of my LinkedIn posts recently, right? And I like to think of it as the velocity of the DB time, right? And so average active sessions is to DB time like velocity is to distance, right? Okay, so what does that mean? Well, let's talk about it. This is really the reason why we had to invent this thing called average active sessions, right? This is circa 2004 Enterprise Manager Perf page, and we charted, DB time per second over time. That's what this chart is, right? But we didn't really have a great name for the chart itself or the units that we were sort of that were being expressed, right? And so we called it sessions waiting and working, which is, very explicit and not untrue. It's basically sessions in wait event or working, waiting or on CPU, right? So this was a conundrum because we had a really important chart. We knew that this was extremely important, but we didn't really have a good name for the measure and the units. And so why was it a problem? Well, the thing we were actually displaying was from sysmetric history, and it was called database time per second. And it was a measure of the total database time in per 1 minute interval. So you could actually see 60 of these at a time. The last hour was divided into 1 minute intervals. And the database time accumulated in each of those 1 minute intervals was divided by a minute, by 60, and that would be the database time per 60 per second, right? So 60 seconds in a minute. So this was really what we were charting, but the raw units were centiseconds per second, right? But then, it's like, well, that's time divided by time. What if we convert them to the same units of time? So all you have to do there is divide centiseconds by 100. And now you're talking seconds per second, right? So, well, like, what is that, right? Seconds and seconds cross out. So you really have a unitless metric here, a measure, a unitless metric. And so what do we call such a thing, right? So it's the most important thing, and it doesn't have units. And so that means it needs a real name. And as we used to do in the old days, we convened, big meetings of people. This was pre-COVID, and the way we operated was, when important decisions needed to be made, you got all the critical stakeholders in a room and everybody hashed stuff out, right? And so there was a lot of brain power in this room. And the objective, and so this is my notebook. This is actually a Xerox of my notebook entry from that meeting. And you can see the subject of the meeting was the perf page and the home page. And these were the pages where we showed this chart that needed the name, right? And so lots of, very important Oracle people were in the room trying to talking about this and other issues. And at one point, we kind of, I remember sort of, we're thinking about different things we could call it, and we talk about centi-users per second, right? And so that's sort of a silly thing, but it kind of steers you towards the concept of user time versus elapsed time, and that user time and users are kind of like, there's a sort of a averaging user time sort of equates to users kind of thing is where we were headed with that. And in the end, the name to me makes total sense. Like, it's like it was really hard to figure out, but in the end, it makes total sense. And over here on the right, you can see I have it encircled in red, right? Seconds per second. seconds per sec, right? So that actually gets at the fact that we had two different things being measured, right? Equals average active session. So that was really the seminal, that was the coinage of that term happened at that meeting. And I believe it was February 26th of 2004, probably. Anyway, so I mentioned this at the beginning. It's the way to think of it is the speed of the database in a certain sense, or how fast it's going. Maybe that's not the right analogy either, because the more DB time doesn't necessarily mean queries are happening faster, right? But the definition is really, average active sessions is total DB time divided by total elapsed time over some interval of time, like an hour, a minute, a day, whatever. So it's the rate of change of DB time over time. And when you say it that way, it should start sounding like your high school calculus, right? So you could say, well, average active sessions is the rate of change of DB time over time. So it's really the derivative of DB time as a function of time, right? Well, then, if it's the derivative, then by the fundamental theorem of calculus, the integral of average active sessions is equal to DB time. Okay. But then again, by our high school calculus, when you plot such a curve that has an integral, then the area under the curve is equal to the integral, right? And so if you plot average active sessions as a curve over time, the area under that curve is actually equal to the DB time. So that's a key thing in terms of understanding these charts that we draw all the time. And we also sometimes refer to as the load on the database. It's sort of how hard the database is working. It's another kind of way to understand it. And so the usage model for charts that depict average active sessions and fill in the area under the curve, well, the area under the curve is the DB time, and we break it down into our three groups, CPU, IO, and wait. And so the amount of paint on the screen is the amount of DB time. And it's very easy to see where the dominant DB time, where the dominant class of time is. It's in the orange stuff, right? The orange is there's a lot more orange on the screen than there is green or blue, right? And that's how you tell where the DB time is. And so the usage model is very simple. You click on the big stuff. When you click on the orange stuff, then you get taken to some kind of drill down that's about the orange stuff. And if you click on the green stuff, you go to a drill down that's about the green stuff, right? So clicking on the big stuff was really the usage model for UX, where the big stuff is proportional to the big DB time, okay? And then we stack these things again for a reason, and we try to maintain these color branding. So we've branded the colors, the DB time colors. We've tried to keep the branding over many years, and I'm happy to say we've been pretty successful in that regard. There's lots of different activity charts, but hopefully they all have green for CPU, right, and blue for IO. So the color is very important, and also the stacking order. CPU has to be on the bottom because we want to compare it to the red line, which is sort of the CPU limit. And now the fungibility of DB time basically allows us to draw pictures like this, which is a picture of a visualization of all the databases in an enterprise managed by Enterprise Manager, where it's in a tree map visualization where the size of the cells in the tree map is actually proportional to the average active sessions. Okay, and so this gets at the fungibility of the ability to compare average active sessions in database A to average active sessions in database B, because it's your time, not the databases. There's nothing different about the DB time in database A than database B, because the time is really the client time. And, this is a pretty useful thing, right? Here's an enterprise that has hundreds, who knows how many databases are hiding in the lower right-hand corner, but it's pretty obvious that there's only one that really matters, right? I mean, King Kong here at the left is responsible for a third or more of the DB time in the entire enterprise, right? All right, so let's talk about ASH. The best way to think and understand ASH, I think, is like a video or a movie, much more like a movie, like the old kind of movie where there were discrete pictures that then get strung together into the movie. So it's really like a film of database activity. And I'm not gonna talk in detail about the mechanism because that's not really that important in order to successfully use ASH and understand ASH, right? But the mechanism is an in-memory circular buffer managed by a dedicated background process. And what that background process does is it wakes up every second and it surveys all the session state objects in the database in the SGA. And these things are basically every foreground that's working on client request has an associated session state object, an area in the SGA. And in that area, that foreground, while it's working on queries, records all kinds of information about what it's up to along the way to answering your questions, right? And so the ASH mechanism wakes up and looks at all of those things and says, what's everybody doing? Everything, every foreground that's attached to the database gets looked at. And if it's actively working on a query, a whole bunch of attributes about from that session state object get written into this circular memory buffer, the ASH buffer, right? And the ASH buffer can contain, a certain amount of that data, right? Going back in time, right? And so the most recent samples will be there and then going back in time until they run out of room. And there's a sort of size limitation the size of the buffer and the amount of activity kind of limit how far back in history it goes. But typically, DBAs should be able to see about an hour. That's sort of like by default the heuristic. And dozens of attributes are captured. And how do we use that? Well, the meaning of these things is really that each frame in this movie counts for 1 second of time, right? And so each sample in the frame counts for a session spending a second of time, doing whatever it was observed to be doing at that time. And so you can count samples or aggregate samples and estimate time, right? Because basically each row in ASH counts for a second, and so you can add the seconds up. And the other way to think about ASH is that it's actually a point in time measure of the average active session function. This sort of, if we think of that as being a kind of an abstract function over time, every time you take an ASH sample, you're looking at a value of that function at that point in time, right? The velocity of DB time at that point in time. And so the basic way that we make use of this is by what I like to call ASH math. And that's simply estimating time by summing up samples. And the simplest form of ASH math is just count star equals DB time in seconds, right? Count samples and just equate it to DB time. A more accurate and more proper way to estimate DB time is by summing up a common ASH called USECs per row or microseconds per row. So each row in ASH has a value for this column that says, okay, here's how many microseconds this sampled value should count for when you're doing DB time estimates, right? And so all the rows in a given sample will have the same value, but for instance, if the sample was delayed for some reason, then the microseconds would count, it would count for more than the last sample, which was not delayed, right? So it's very subtle. But the important thing is how you group the aggregates, right? So you're doing count star or sum, that's not so interesting until you start doing group by, because when you group by, now you're just slicing and dicing DB time by various dimensions. And that's a very powerful thing to be able to do. That lets you analyze database performance from bazillion different angles. And ASH, you're using ASH in a kind of a statistical manner, which means that more samples the more you're aggregating, the more accurate or the more you're kind of believing the conclusions you can draw, right? If you're saying that if you're looking at three samples and two are on CPU and one is in an IO weight, and it's a pretty dicey thing to say that your workload is 30% IO, right? You've only observed three samples and two are CPU, one was IO. Okay. If you got 3,000 samples, right, and it's the same ratio, then you're much more confident in your statement. And on the right, we just sort of show an example of the kind of SQL you do to apply ASH math, right? So here we're looking at active session history, and we're grouping everything by minute of the day and SQL ID. And we're computing total DB time in microseconds, and then average active sessions by dividing total DB time by the number of microseconds in a minute, because all the intervals are presumed to be 1 minute. So that's kind of how we do those things. So let's get into the calculus thing a little bit more, right? So it's just sort of like why ASH math works is really a matter of calculus. So again, if we imagine our active session curve function of time, right? The the integral of that is the DB time. The area under that curve is what we're interested in from a DB time point of view, right? So if we overlay onto this curve ASH samples, right? Every stack of red dots is one sample, one ASH sample, and each of the red dots is an active session. So sometimes there's more active sessions, sometimes there's fewer active sessions, but basically every second we're taking a reading of this active session function, right? We said that's kind of what ASH is in a sense. Well, if you kind of draw these rectangles and then realize that, this sort of is what we used to do in our high school calculus book, what we called a Riemann integral estimate, an estimate of the Riemann estimate of the integral, right? And so in the case of ASH, delta t, the space between samples is 1 second, right? And so, the number of samples, if you wanted to add up all these rectangles, what would you do? Well, you would multiply the number of red dots times the delta t, right? And then plus all of them in succession. But delta t is 1, right? So everybody's getting multiplied by 1. So really all you're doing is adding up the number of red dots altogether, right? And so that's why we say count star equals DB time. The total number of red dots equals the total number of DB time. I mean, total amount of DB time in seconds, right? So, that's kind of why ASH math is related to, again, sort of a calculus concept, estimating the integral by, adding up these slices of the function. And so it turns out that estimating DB time and measuring DB time agree quite closely when you plot them separately, right? And so here we have some screenshots from, again, quite old versions of Enterprise Manager when we had two different pages, one sourced exclusively from time model data, that's on the bottom, and another sourced exclusively from ASH data, and that's on the top, right? And so both of them plotting average active sessions over time. And so it was actually very useful to be able to compare these two things, because you're looking at a single story told by two independent instrumentation sources, okay? And sometimes, so when that story agrees, then you're pretty sure it's the truth, right? And so it's just like if you only listen to one person, then you got to accept what they say is true, right? But if two people both separately tell you the same thing, it's a much more confidence building thing, right? So that's the value of this. And conversely, sometimes they don't tell you the same story. And then it becomes very important to say, okay, what's going on here? Why don't ASH and time models seem to agree? The other interesting thing on this screen to note is that the effect of averaging. Okay, so the bottom chart has 1 minute granularity. There's 1 minute between each data point, right? In the top chart, the one based on ASH, the bottom one is based on sysmetric history, which is 1 minute sysmetrics. The top one is based on ASH, but aggregated into 15-second buckets, right? And so you can see the top chart actually goes all the way up to 12.7 active sessions. The bottom one only goes up to 9. Why is that? Well, the bottom one is summarizing 4 15-second intervals, and it looks like only 2 15 seconds actually got up to 12.7. And the other two were considerably less. And the average of the 12.7s and the considerably lesses amounts to about 9, right? So that's always, something to know about, sort of ASH calculations in a way, or the interval that you aggregate over kind of can affect sort of uh, kind of the height of these peaks that we see. So we talked about CPU saturation causing problems with weight event instrumentation, right? And so is there anything we can do to kind of figure this out, whether we have the problem, especially if we don't have access, let's say, such as in the cloud, to the actual operating system itself, right? If you got a cloud database, the infrastructure is not something they let you see, right? Well, it turns out you can at least you can do some guessing, right? And so you can compare ASH and time model in terms of what they say with respect to CPU. And why is that? Well, in the time model, as we discussed, the DB CPU is actually fetched from the operating system. It's not measured in a stopwatch, and it's not affected by run queue. It doesn't include any run queue time. Whereas in ASH estimates, when you sum up the microseconds per row for all the samples that are on CPU, you're estimating CPU time. But if the session is on run queue, it'll be exposed in ASH as if it was on CPU. So ASH CPU estimates include run queue time. Time model DB CPU does not. So if you subtract those one from the other, time model from ASH, because ASH might be bigger, right? And you get a value significantly greater than 0, and you don't look for exactness here, you may have a CPU saturation issue. And you can do a similar calculation just using time model and weight data, right? Where you basically take total DB time, which will have run queue in it, and you subtract uh, all the wait time, which also might have run queue built into it. But if you also then subtract DB CPU, which won't have run queue in it, then anything extra is likely run queue. And so that's actually the sort of the formula we use in Enterprise Manager to estimate CPU weight. So in Enterprise Manager, when it says CPU weight, that's an estimate. It's a conclusion that we make by doing this kind of arithmetic. But it turns out it's a pretty good conclusion. And this is a screenshot I got from a very experienced DBA. And he was questioning EM, showing this huge pile of CPU weight. All this light green stuff is CPU weight. And he's like, well, how can that be? Because it's not even, the dark green is the actual CPU, and it's not even pushing up to the red line. So how can I have run queue, right? What's that about? Well, above there, you can see the load average kind of reflects the same big hump. So that's sort of, there is something going on with the CPU. And it took him quite a while. I didn't have much to offer other than, this is how we compute it. And so, that's why it's showing up as light green. But he eventually figured out that there was a configuration issue with some kind of NUMA stuff, which has to do with, sort of scheduling and operating system things. And that's what the source of the problem was. There actually was a whole bunch of time spent, schedulers thrashing. So the estimate turned out to be, accurate, and this was a real picture of what was going on. All right, we're in the home stretch. Let's talk about performance monitoring. And we're going to get mathy again a little bit. and talk a little bit about something called Little's Law. But before we do that, let's just think about the database and performance analysts. They often talk about queuing theory and queuing systems, right? And so the Oracle database is kind of like a giant tangled web of queuing systems, right? So let's just sort of run through some of the examples. So at the highest level, client requests come in and foreground processes process the request. And that's sort of a description of a queuing system, right? The foregrounds are the queuing service centers, and the clients are sending requests as SQL and getting answers. But it's a pretty dynamic thing, right? The number of connections can go up and down, and sometimes it can go up too fast and all these other things. Uh, but but that's one level, right? So all of these foreground processes, well, they also sort of have to access CPU resources, and those are effectively queues, and they're really kind of the most important queues in the system, right? That's really where the crunching happens. So CPU resources are queuing centers managed, and threads and cores are managed by the OS, and foreground processes, compete for time of those services. But then even more, the foregrounds all connect to the SGA and share data structures, things like buffers and execution plans and all kinds of other things through various complex software mechanisms and system calls and sort of serialization mechanisms like mutexes and onqueues and latches. So these are all sort of effectively kinds of queues, right? And so the bottom line is it's kind of like queues all the way down, right? It's a complex, highly dynamic, multi-layered queuing system. Every single execution of every single SQL could theoretically take a slightly different route through this very complex thing. But it turns out that in aggregate, even very complex queuing systems, when they're in a sort of a stable state, they can be modeled using a very simple formula called Little's Law. I don't know much about Little other than, Little's Law was named after him. He presumably described it or discovered it for the first time. So Little's Law says that, under steady state, queuing systems in steady state will obey the following equation. The number of clients in the system will be exactly equal to, on average, so these are all averages, so steady state meaning, the average over some extended period of time, indicating that things aren't changing a lot. On average, the number of clients in the system will equal the arrival rate, the rate at which requests are being asked of the system, times the average latency per request, right? So, how fast requests are coming in times how fast requests are being serviced. The product of those two numbers is actually equal to the number of clients in the system on average. And you can, kind of look it up. This guy, Neil Gunther, is well-known sort of performance guru, and he's got a lot of interesting things to view, and especially about queuing theory. He's got a lot of stuff. Anyway, what's this have to do with what we're talking about? Well, it's directly related to what we're talking about. It turns out that Little's Law average active sessions is just like L in Little's Law. And lambda is just like user calls per second. And W is just like DB time per call. So average active sessions in the system is equal to user calls per second times DB time per call in seconds, right? Why in seconds? Well, because then calls per second times seconds per call, cancel, unitless measure. What is that unitless measure? It's average active sessions. And so the key thing here from a performance point of view is that we monitor average active sessions. When the system is stable, it should show statistical stability. It's not going to be a flat line, but it's not going to go zooming up and zooming down, right? The system is stable, it'll jiggle, but it won't jiggle a lot. But when it booms up, right? Well, how did that happen? Well, it was probably, since that thing, average active sessions, is the product of these two things, one or the other of these two things could drive it up, right? If there's an increase in calls, it could drive up average active sessions, or if there's an increase in average latency per call, it could drive up average active sessions, or of course both. So there's three possibilities. And in performance, like in scalability analysis, what you're trying to do is figure out, how far you can push increasing calls per second before the response time goes through the roof, before DB time per call goes through the roof. And so if there's a big change in average active sessions, it's probably either a demand surge or degraded response time. And that's exactly why this is such a useful visualization, right? Because here we see, a relatively stable system, a fairly consistent mix of CPU and IO, and not challenging, the red line there. But every once in a while, in this view, four times exactly, average active sessions goes through the roof and it's all red, right? Well, that's a performance problem. It's not too hard to figure that one out, right? And that's why this was such a popular tool. And it's still basically the model that we use. And so you can do kinds of performance analysis at scale and even without even seeing a whole lot of detail, right? I just did a kind of a Google image search and got some average active sessions, top activity screens, but you can tell a lot about what's going on by looking at these things. There's a lot of sawtooths of CPU, so that's kind of some kind of seasonal workload or seasonality in the workload. There's a few that look like they could benefit from Exadata, make the blue stuff go away. This guy in the middle is having a really bad day, right? It's just a big block of orange, right? Nothing is going on, and everybody's doing nothing, waiting, waiting, waiting. And that's the kind of analysis you can do very quickly when you know what the screen means and what the colors mean. Um, and so this is what it looks like today. So this is the great great grandchild of the screens, of the portrait gallery, and it looks very similar. This is an EM24 AI. This is brand new. Looks nice. Happy to say the color scheme has been maintained. Similar, this is EM24 AI Perf Hub. Again, the tree map drilled down into ash.
Right now, there is a question, actually more so of a comment from a customer. For Little's law, the W can actually be a function of lambda when user calls rate become too big, that it actually causes each call to take more time than before.
I mean, we're not trying to do a deep dive on, this person sounds like they might be a Neil Gunther student, right? But yeah, I mean, the point is really, uh, you're either asking more or you're getting worse response time when average active sessions jumps, right? The usual, a very rapid jump in average active sessions is almost always going to be due to a performance incident in the sense of degraded responses. I mean, unless it's just a thundering herd incident, which can kind of induce those kind of problems itself, right? But anyway, good point. I mean, yeah, we're not trying to be deep queuing theorists here, but I take your point.
JB, you're not seeing it, but you're getting applause and hearts and thank yous. Um, so I think people are enjoying all you had to share.
The things that people should always have in the back of their minds when they're doing performance analysis, they should be always thinking in terms of these concepts, right? Or if they're using Ash, understand what it means to estimate DB time and the limitations that there can be, small sample sizes is less meaningful than large sample.
The single most valuable tidbit, according to someone, was the measured disk access time includes time on the run queue.
All right.
Well, listen, everyone, thanks again for joining this call. Anything else, let us know. Have a great rest of your day. Thank you, JB, for such a great call.
All right, thanks. Cheers.